Alright, our next chapter, alkyl halides and nucleophilic substitution. Elimination will be the next chapter. So we might already know some of this. There are three major classes of halogenated compounds. We've been talking about alkyl halides for a while because we've been learning about alkyl groups. Here's ethyl bromide. That's a halogen bonded to carbon that's fully saturated with hydrogens, or is sp hybrid. A vinyl halide, maybe suppose I should say vinyl. A vinyl halide, carbon is sp2 hybrid that the halogen is bonded to. We might have aryl halides, bonded to a carbon on a benzene ring. So alkyl halides are like a functional group. A halide is a functional group, just as a double bond is a functional group. An alkane is not a functional group. The halogen is more electronegative than carbon, so it polarizes this bond. We might say there's a partial positive charge on carbon here, and that's due to halogens being more electronegative, or having lots of electronegativity. So that makes this carbon susceptible to nucleophilic attack. Typically that's something with extra electrons and it's looking for a nucleus of an atom, carbon's nucleus. And this halogen can leave with an electron pair. I would draw a double-headed arrow with this bond jumping on the chlorine. And this should be somewhat of a review. I told you earlier we didn't formally go over chloral or bromo or fluoro or iodo, but that covers all of them except for element At. So now you know how to name those halogens as a substituent. So our IUPAC convention for naming alkyl halides, same as always, we find the longest continuous carbon chain, even if the halogen is not bonded to any of those carbons, like it is over here on this one, where we have a 7-carbon chain. So over here, a 4-carbon chain. The halide, which is chlorine, is on the 2nd carbon, so we call this 2-chlorobutane. Here we have our 7-carbon chain, a derivative of heptane, and now we want to use that complex substituent convention we learned earlier, where this is an ethyl, and we start numbering number 1 where it's connected to the chain, so this makes this a 2-fluoryl ethyl. So just this gets the name 4 parentheses 2-fluoryl ethyl heptane. So up here I see a long carbon chain. I'm going to start numbering from this side because I see this substituent occurring sooner than starting over on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9. So a derivative of nonane. Carbon number 6, I got the bromine. Carbon number 2, I got the methyl group. So this becomes 6-bromo-2-methyl nonane. So here we could have left the hydrogens out, but of course this shows stereochemistry. Never goes away. Both halogens are on the same side of the ring. And I might think I either got to start 1 over here and come over to 3, or start 1 over here and come over to 3. I'm going to start 1 here just because B before F alphabetically. So this becomes cis 1-bromo-3-fluorocyclohexane. To me, my heading looks like a contradiction. Systematic common names. IUPAC is what I think of being a systematic system for naming things. Nevertheless, the alkyl group is a substituent on a halide. It's useful for small alkyl groups only. So here's that isobutyl group. Isobutyl bromide, sec butyl bromide, tert butyl bromide. And you should know this. If not, go watch the video on it. So you learn your alky groups early. It'll help you all semester long. So here's something new. Common names of halides. And you'll notice this is only one carbon. All of these. We might call this methylene halide. The CH2 is called a methylene group. CH is called a formal group. So we call this methylene halide. Carbon tetrahalide. Well, let's just put a specific halide on there. Chlorine. So methylene chloride. That's what everybody calls this. Nobody, unless you're asked on a quiz, what would be the IUPAC name? Dichloromethane. Nobody says dichloromethane. Everybody who's a chemist, anyway, says methylene chloride. Likewise, not too many people say trichloromethane. We say chloroform. And likewise, this is going to be called carbon tetrachloride. The IUPAC name would be tetrachloromethane. Now, since we know sec-butyl and tert-butyl, we know what primary, secondary, and tertiary mean. So we can classify our alky halides the same way. We have methyl halides, where the halide is attached to a methyl group. We have primary alky halides, which that halide is on a carbon that is only attached to one other carbon. Well, it could be attached to a long chain, but it only has one carbon attached to it. Secondary alky halide, carbon to which halogen is bonded is attached to two other carbons, and a tertiary alky halide. So knowing what type of halide you're dealing with is important for predicting what type of substitution and elimination reactions occur. So here's our methyl halide. Here's a primary halide, secondary halide, and this R group could be a big long chain. Point is, this carbon is bonded to two other carbons. Tertiary alky halide here. This halide is bonded to a carbon that's bonded to three other carbons. Makes it tertiary. Well, if we have two halides, we can talk about different types of dihalides. A geminal dihalide, two halogen atoms are bonded to the same carbon atom. So we call this a geminal dibromide. And this is a vicinal dichloride, where the halogen atoms are on adjacent carbon atoms. Vicinal, and so we should be able to predict the trend in electronegativity from the periodic table. Increases from bottom to top. So that means fluorine is the most electronegative, followed by chlorine, followed by bromine, followed by iodine. And it says bond length increases as the size of the halogen increases. And once again, we should be able to make that size prediction from looking at the periodic table. These numbers might be interesting. We won't spend any time on those numbers. Alright, we got to spend time on these numbers. One might say, well, why isn't the carbon fluoride bond have a larger dipole since it's more electronegative? I think it has to do with size. Notice it's kind of a wash. It turns out this one has slightly larger dipole. They're about tied. Other than that, we see this trend going on. The part we care about is this last point here. Molecular dipoles depend on the geometry of the molecule. So how many of you from Chem 1 like to predict whether a molecule was polar or not? Just as I expected, nobody does. That's why you take organic chemistry where you visualize 3D shape and you get over that learning disability. So carbon tetrachloride, even though these bonds are polar, the overall molecule has no dipole moment. It's a very nonpolar solvent because of the symmetry. All those polar bonds cancel themselves out. You can think of these as being vectors. They're all the same magnitude and they cancel each other out. More Chem 2 stuff. The greater the intermolecular forces, the higher the boiling point. Dipole-dipole attractions are not significantly different for different halides. London forces are greater for larger atoms. That means the higher the molar mass, the higher the boiling point, and spherical shape decreases boiling point. Notice these are what type of isomers? Maybe they're not isomers. No. 3 carbons and 1 more make 4. 3, 1 more make 4. They are constitutional isomers. So here's something that's important when you go into the lab and you do an extraction and you want to know which layer is the alkyl in. Well, we're going to say it's in the organic layer, but where is the organic layer? Is it in the top of the separatory funnel or it is in the bottom? Alkyl fluorides and alkyl chlorides with just 1 chlorine atom or fluoride are less dense than water, which has a density of 1 gram per mil. Alkyl chlorides with 2 or more chlorine atoms are denser than water. So methylene chloride goes to the bottom of the separatory funnel and the aqueous phase will be on top. Alkyl bromides and alkyl iodides are denser than water. So how would you make an alkyl halide? Nobody's raising their hand. Free radical halogenation. I studied the reaction mechanism. So one way to prepare alkyl halides is free radical halogenation. Chlorination produces a mixture of products. We saw the 60-40, 1 chloral and 2 chloral propane. And then we saw that bromination of propane was a lot more selective. It was like 97 2 bromo and only like 3% 1 bromo. So here's a new method, free radical allylic hydrogenation. We will find out what the allylic group is. The halogen is placed on a carbon directly attached to a double bond. That makes it allylic. So I just mentioned bromine being more selective, and I was looking at the slide the other night and I'm like, well, why didn't they put isobutane up here so we can compare the difference like we did with bromine and chlorine when we looked at propane? And I said to myself, why do we have only 50%? And here's 90%. And the reason why is it's a lot harder to stop this thing from putting on another chlorine. So under optimal conditions, if we want just the monochlorinated product here, you're only going to get about 50%. Where down here, it's a lot more selective, and you're going to put it and get the T-butyl. And that's because a tertiary radical is so much more stable than a primary, which is what you'd have to do to stick it out here. Notice all of these, you're going to have a secondary radical. So now we get to learn what the allylic position is. The allylic position is adjacent to a double bond carbon. So here's 2 carbons double bonded. Any carbon adjacent to those 2 is the allylic position. So we can call these allylic hydrogens. And in bromination, that's where the substitution occurs. So the mechanism, hopefully you could come up with it. There's an initiation, and bromine turns into 2 bromine radicals. Bromine radical floats up here. We have homolytic bond cleavage, form our HBr, and notice this radical here. I could draw it jumping there and another one jumping there. They don't show it in the slide. These are the 2 resonance structures. And then this thing could just as easily attack. Of course, you'd get the same product because it's both at the allylic position. You can't tell the difference yet. In the future, we'll have some other groups, and you can see how the double bond can move on you. Both allylic radicals react with bromine. N-bromosuccinimide is a mouthful to say, so we like to say NBS. And so what you want to do is when you see NBS, think to yourself, well, that's a reagent that puts a bromine on some molecule. And what it does is you can form this bromine, which will next undergo a free radical bromination reaction in very low concentrations. Because you mix this in a flask with what you want to brominate, and then you slowly drip in HBr. Each time 1 molecule of HBr goes in, you create 1 molecule of Br2. And then that goes on and reacts, so you can keep the concentration of Br super low. So this slide might help you with the Chapter 4 online homework. What is a substitution reaction? Here's a halide. So we have our alkyl halide, and this bond is polarized. Think about a partial positive charge on carbon. This nucleophile is looking for a nucleus, slams in there, that leaves, and there's the substitution. The nucleophile gets substituted for the halide. Elimination gets split into our next chapter coming up. But alkyl halides can also undergo an elimination reaction. What gets eliminated is the hydrogen and the alkyl halide. And the base grabs the hydrogen, and then this bond collapses, and you get the alkyl halide. The similarities in both reactions is the alkyl halide is called a leaving group. So the SN2 reaction, the S stands for substitution, the N stands for nucleophilic, and the 2 stands for bimolecular. I'm going to repeat all that in the next slide. So here's our nucleophile. Here's our alkyl halide. We like to call that the substrate. Nucleophile, substrate. This thing seeks out a nucleophile. The leaving group leaves, and we get methanol as a product and iodide as a product. And if we're thinking about this, you just don't have hydroxide in a bottle. You normally have something like sodium hydroxide, potassium hydroxide. So there's some counter ion, potassium maybe. Over here there'd be some potassium ion. Over there, what do we call those ions? It's another favorite of Gen Chem students. It starts with the letter S. Think about team sports. No one's shouting it out. Spectator ions. Spectator ions are omitted. So here is a mechanism with our curved arrow formalism. Curved arrow start at electrons, go to atoms. So this curved arrow is starting at the electrons in the bond, goes to the iodine atom. Here is a transition state. What is a transition state? We can describe it in terms of an energy diagram, which I was hoping some of you would shout out where that is on the graph. But we'll go over this. It's where bonds are forming and bonds are breaking. The carbon-oxygen bond is forming, carbon-iodine bond is breaking. Alright, so I said it was bimolecular nucleophilic substitution. So the bimolecular Molecular, we know by studying the reaction kinetics. So here's a rate law, and it says the rate is equal to some constant times the concentration of alkyl halide and the concentration of nucleophile. So if I double the concentration of alkyl halide, what do I do to the rate? It doubles. If I double the rate of the nucleophile, it doubles. So that tells us what's possibly going on. All right. So here's the transition state. It's the highest point on this curve. This bump here, if I knew this energy, I'd call that the activation energy. And two species have to be involved. That's why it's bimolecular. So what good is a SN2 reaction? I like to tell people alkyl halides are basic building blocks. So X is any halide, normally chloride or bromine. What can I use for a nucleophile? Well, here's a pretty good list. So I can make an alkyl halide. If the nucleophile is OH, I can make an alcohol. If the nucleophile is an alkoxide, I can make an ether. If it is a sulfur, if it's a sulfide, I can make a thiol. If it's got an alkyl group, I make a thing called a thioether. I think I might have misspoke calling this a sulfide. We can make amines, make the amine salt. So all these different groups. If I have a cyanide group, I can make a nitrile. If I have a group like this, I can make an ester. All these things can be formed.